Let's start. Welcome back, folks. Thanks for coming back. There's good news and bad news. I guess they're the same news, which is we're going to be doing work for the rest of the course, so it's on the blackboard. No more of these slides and movies and that sort of thing. So if you're coming for more movies, sorry. Otherwise, great. Today's goal is I want to define Khovanov homology. That and its variants are the main tool / topic for the course. And then the S invariant, which is a number that you can get out of Khovanov homology or a variant of it. We'll talk about properties and applications of the S invariant in 2 weeks. In particular, the headline theorem I'm heading for is that there are 4-dimensional spaces that are topologically the same as R4, but not smoothly the same as R4. In order to get there, there's another ingredient we need, a theorem of Friedman and Quinn, Friedman and Quinn, about knots, topological disks. So we're going to do that next week. So the material from this week we're going to sort of not use next week, then we use a week after. So the plan today is I wanted to define Khovanov homology, I wanted to find the S invariant. I sort of wanted to start there, but I just couldn't bring myself to do that because Khovanov homology would have seemed completely unmotivated. So I'll start talking a little bit about, just for a few minutes, about knot diagrams. That's just background, and the Jones polynomial. So this is Judah von Jones from, I don't know, roughly 1983. And the version that I'll talk about, I mean, the construction I'll give is Judah Lou Kaufman. I don't think Jones was a student here, but Kaufman was a graduate student here back in the 60s. So we'll do that for a few minutes. So instead of Khovanov homology seeming completely unmotivated and mysterious, the Jones polynomial will seem completely unmotivated and mysterious. But that's actually how the world is, at least at the moment. So that's probably good. So a little bit more, so more background. My recollection is that writing in the shadow is OK. Louis, you can see that? Good, thank you. And if the writing gets too small or I'm too quiet, somebody should tell me. If I'm too loud, too bad. A link is just a finite union of disjoint knots. So for example, OK, well, that'll be fine. We're just drawing links anyway. There's an example of a link. They don't have to really be twisted up. They could be disjoint from each other. I don't know. There's another link. I mean, they could be not linked with each other. That's fine. Of course, these are 3-dimensional things. It's in 3 space. I'm not drawing the link. So all links can be represented by link diagrams, which is what I've been drawing. So what's a link diagram? It's just an collection of immersed circles in the plane, smooth circles in the plane, but that are allowed to cross over themselves or over each other, I mean, pass through each other, through themselves. So like this thing here, this is really this curve in the plane. But then I remember at the double points which was on top. So I've indicated which is on top of the little crossing information. OK. So I guess this was a theorem that all links can be represented by diagrams. That requires that they be locally flat, like we were saying during the lecture last time. That's part of my definition. OK. And the second classical theorem I need is Reidemeister's theorem. Which is that if 2 diagrams represent isotopic links, that is the same, our notion of the same. One can be formed the other day. We represent isotopic links. The diagrams are related by a sequence of just moving them around in the plane. So those are planar isotopies. So that's like I had, I don't know, a diagram like this, and you just wiggle it around, but without changing any essential way in the plane. Okay. Planar isotopies. And then the following three local moves, local changes in a disk. So here's a disk. This is distinguished lecture, right? So they have some distinguished lecture chalk fresh on the table. It's really good service. So you can introduce a twist or remove a twist like that. You can introduce cross one strand over another. So, or the third one is you can bring a strand under or under a crossing. So let's see. And by doing a sequence of these moves, if you had two diagrams that represented isotopic links, you can turn one into the other. So in some sense, the subject is combinatorial. Of course, it might take a lot of moves. There are bounds on how many, but the bounds are ridiculous. Like, you know, I've forgotten what they are, so I won't try to say how ridiculous, but they're big. Links can be oriented. So an oriented link, just you choose a direction around each component. So here I'll orient this link. We'll go around this component this way, and that component that way, and this component that way. Okay. And implicit in what I just did, these oriented links have oriented link diagrams. And there's an oriented version of Reidemeister's theorem, so there are oriented Reidemeister moves. Oh, I don't think I'm going to want this later, but this is Reidemeister move 1, this is Reidemeister move 2, and this is Reidemeister move 3. Just a little bit more crossings. So for oriented links, there are two kinds of crossings. For unoriented links, there are only one. So you can have a positive crossing. That's a positive crossing, or a negative crossing. This is a negative crossing. Here, x goes over y, and there y goes over x. Okay, so positive is x over y. For unoriented links, the other thing I need about crossings is there are two ways to resolve a crossing. So given a crossing like this inside a disk, without changing the diagram outside the disk, I can eliminate the crossing in two ways. I can eliminate it like this, or I can eliminate it like this. And I'm going to call this the zero way of resolving the crossing, and that is the one resolution. So this is the one resolution, and that's the zero resolution. Now, this tends to, many of you have seen knot theory before, have seen what I'm talking about before, and so you're not bothered, but other people this tends to bother. So let me explain that these are not the same by doing an example. So here's they are not isotopic Rel boundary.
What do you mean when you say resolution?
Oh, I just mean, yeah, great. I take the piece inside this ball or in this disk, and I replace it by this or that. Completely changes the knot.
The right-hand side and the left-hand side.
Totally different. Totally different. In fact, one of the two will always change the number of components. So they don't even have the same number of components. Sorry, both of the two. Both of the two. So for example, if I take this, so I've got two crossings. Maybe this is crossing A and crossing B. And for each of the two crossings, there are two ways I could resolve it. So I could do the 0 resolution to both, the 1 to the first and the 0 to the second, the 0 and the 1, and the 1 and the 1, or the 1 and the 1. So I'm going to just recopy this picture 4 times. And now, I had the eraser. Let's see, which was 0? 0 meant you were walking along the top strand and you turned left. So if I do the 0 resolution here, that connects these up like that. And if I do the 0 resolution here, it connects them up like that. On the other hand, if I do the 1, it connects up the other way. And the 1, sorry, this is still the 0. If I do the 0 and the 1, very good, this way. And if I do the 1 and the 1, looks like this. Okay. Let's go back this way. I probably say this every time I speak in this room, which is more often than I deserve. There's this amazing technology that we have here of these moving blackboards. But Princeton's sort of old university figured out only half of it, which is it's useful if both the front and the backboard move. Someday, some donor will donate money to Princeton in order to have proper moving blackboards. But this is not that day. I would love to be that donor. I have a guess what it would cost with the donor relations. You get me a good price, I will be that donor. So here's the Jones polynomial. It's called V. That's for Vaughn, Jones's first name, I assume. I'm going to write a formula, and everything in the formula basically is not going to make sense. Like I'm not going to want to define it. I'm going to define each of the things. The formula will do an example, and it'll all make sense. But let's have the formula first. He says minus 1 to the, except I have to cheat. N minus, right? Yes. Okay. Q to the n minus 3n minus. Of minus q to the absolute value of v times q plus q inverse to the absolute value of kv. OK, and as promised, nothing here is clear what I mean. So let's just go through and define all of the pieces. This is a polynomial in q and q inverse. So it's not really a polynomial. It's a Laurent polynomial. N and n minus. Sorry, I had chalk. N. N is just the number of crossings. And n minus is the number of negative crossings. OK, so back over here, we had 2 crossings. Of them, OK, I need to choose an orientation. In the end, it doesn't matter. If we look at these, this is a positive crossing, and that's a negative crossing. So n minus is 1. 0, 1 to the n. Well, I mean, you know what that is. This is n tuples of zeros or ones. those are these vectors I was writing here. So those are my 0, 1 to the n. Whew. Absolute value of v. This is just like the Manhattan norm of v. So absolute value of v, I just mean the sum of v. So for example, absolute value of the vector 0, 1 is 1, 0 plus 1. One more. Absolute value of kv. This is the number of circles in the v resolution. What? So here I have drawn this thing is k0, 1, and absolute value of k0, 1 is 3. I think I've defined everything. So I'm now going to compute it. So let's do that. So in that example, we had minus 1 to the 1, q to the 1 minus 3. Sorry, 2 minus 3, good counting, 2 crossings, times. OK, we just go over each vertex and write down the corresponding thing. So minus q to the 0 plus 0, I'm doing the bottom left vertex, times q plus q inverse squared. There were 2 circles in the bottom left vertex. So I've now written down the term that corresponded to this. I'll speed up very slightly. Minus q to the 1, q plus q inverse. Let's do the 1, 0 vertex. There's 1 circle, plus minus q to the 1 times q plus q inverse cubed plus minus q squared times q plus q inverse squared. Right. I didn't check before the talk if your degree can be rescinded for being unable to expand polynomials. But this is a slightly stressful moment. So we get q squared plus 2 plus q to the minus 2 minus q squared minus 1 plus, oh gosh, that's a q cubed, but there's another one there. So sorry, that's minus q to the 4th minus 3q squared minus 3 plus q to the minus 2 plus q squared times this. So it says q to the 4th plus 2q squared. Yeah, I do. You see? Good catch. Thank you. Plus 1. Isn't this really exciting? This is what you signed up to come to this afternoon. OK, I can cancel that minus 1 and that 1. Let's see, anything else cancel? One sort of hopes so. 2q squared. Let's ignore those. Here's a q to the 4th and a q to the 4th. Those cancel. Minus q to the minus 2 plus q to the minus 2. Oh, here was a q squared and a q squared. This is getting a little bit hard to read, so let's just write that out again. Minus q times, let's see, 2 minus 3 minus 3q squared plus 2q squared, which is minus q times minus 1. That's great. Negative 1. That's much better. Thank you. Minus 1 plus q, sorry, minus q squared, which is q plus q inverse. Thank you. Well, with some audience help, we got there. It's sort of amazing. I mean, you know, if somebody wrote down this formula and said, this formula means something, you would say, don't be ridiculous. Of course, that formula means nothing. But then you do this example, and it's so much cancellation. It must have meant something. Of course, if I took just the trivial diagram for the unknot. Let's try applying the formula. Where's the formula? Let's try applying the formula there. This would be minus 1 to the 0 and minus the 0, q to the 0, sum over, OK, there's only one term if you take 0, 1 to the 0, one way of choosing no elements. And that gives me minus q to the 0 times q plus q inverse to the 1, which is q plus q inverse. So with much less work but more confusion, that applied to this diagram gave us the same answer. Yes?
When you say circles, do you mean number of connected components?
Connected components. Good question. It's the same because I've gotten rid of all the crossings. So they're all unknots. Yeah, so there's no interesting knotting left at this point. Good question. More questions? OK.
What does the K stand for? VK?
Oh, K was my knot. I didn't tell you. That's the knot. Yeah. You see, I said I defined everything and I lied. This is the knot. And so you can sort of guess, like, the next theorem. Again, this is due to, I'm not going to be, in the later part of the talk, I'm not going to try to give attributions for everything. It gets a little bit complicated towards the end because I'm doing things in a slightly different way from how they develop. But here it's easy. So Jones, except this version due to Kaufman, Vk of q is invariant under Reidemeister moves. Hence, is an isotopy invariant of knots. I mean, I think I just erased the Reidemeister moves. They were here. But you could imagine seeing, well, how does this change if you introduce a new crossing or do a new pair of crossings? It's pretty easy to check that this doesn't change much, and so you got a knot invariant. This is completely unsatisfying, right? It doesn't, I mean, if you've seen the Jones polynomial before, maybe you've been brainwashed. But otherwise, you're wondering, you know, really, like, that's the best I can do, and also, what does this thing mean? And so this is completely unsatisfying. The Jones polynomial arose from, you know, there's some backstory how Jones came up with it, studying, you know, type 2 factors, von Neumann algebras. But basically, he noticed some things that were invariant under Reidemeister moves. I mean, that's not exactly right, but that's approximately right. And so he had a knot invariant. I believe, I claim, this is sort of fighting words, I claim the following is open. Give a mathematically precise definition of Vk of q, the Jones polynomial, that doesn't use a knot diagram. I mean, there are ones that don't use exactly this, that you can give it in terms of braids. But of course, a braid comes with a knot diagram. So really, you're just using special kinds of knot diagrams. I think all of the known definitions somewhere trace back to having a knot diagram. There's no intrinsic construction of this thing at the moment. Feel free to write to me, especially online people, when you disagree with me. But I still think I'm right. So we don't really understand this. This compares unfavorably to the Alexander polynomial that I'll talk about next week, which we understand much better. And maybe this is why people didn't notice the Jones polynomial for a long time. The homework, there's homework on the web page. It gives some additional motivation for the Jones polynomial. It helps a little bit with believing this was a reasonable thing to construct, but it doesn't help very much. Sort of a miracle. Again, this could have been written down by, like, Tate in the 1800s. He just, you know, why would he have written down this formula? It still had a lot of applications, particularly to questions related to diagrams. Let me tell you one before we move on, because everybody should know one. So this is a theorem of Kaufman and independently Murasugi and independently Thistlethwaite from 1987. Any non-stupid alternating diagram is minimal. So I'll just spend a minute telling you what I mean by all of the words there. Here's, if we're lucky, the figure 8 knot. Here's a knot. This is a knot diagram. It's alternating. That means if you walk around, you go over, under, over, under, over, under, over, under, over. Got back to your slides. You're alternating going over and going under. Okay, so alternating, check. Minimal. There is no diagram with fewer than 4 crossings. This has as few crossings as possible. It's an amazing theorem. For example, that tells you this is not the unknot and this is not the trefoil, because those have fewer crossings. It's an amazing theorem. Generally, it's very hard to compute the crossing number, but for alternating diagrams, it's easy. Non-stupid. There's an obvious way you could make this, you could make an alternating diagram that has a simpler diagram in it. You take some diagram and some other piece of diagram, sort of grab a little piece out of one, a little piece of the other, and you just cross one over the other. Okay. Then you can make it simply just by flipping half of the diagram. Okay. That's a stupid diagram. If you can't find a flip like that, so what is a flip like that? It's just a circle that intersects the diagram and only that crossing. Then it's a non-stupid diagram. So the technical word for this crossing is nugatory, and that means the word I should use there is reduced, but you might think reduced had some meaning. It just means unless there's an totally obvious way to reduce the number of crossings. Okay? That's a really good theorem. This was conjectured, in a sense, by Tate, not the Tate that you might know recently, but the Tate from the 1800s in like 1898-ish, where I conjectured he wrote down like a list of things that he said were true, and this was on the list of things he said were true. And many of them were true, and some others were not true. Okay. His papers are really amazing, so I'm not criticizing, but they're not quite in the modern style. This is the end of section 0. Questions? Yeah, it's producing the Jones polynomial. It's pretty easy. Yeah. So there's a nice book by Licorice on knot theory, which introduced the Jones polynomial as a reference on the web page, and it has a nice proof of this theorem. So it's not especially hard from the Jones polynomial. Yeah. More questions?
This theorem is about the diagram at the end of the day.
It is.
Can you give some intuition about how much information is actually intrinsic information is contained in the Jones polynomial? I don't know if there's a good answer to this question.
So the question was, what intrinsic information is there in the Jones polynomial? The answer is it's not well understood. There are some connections to hyperbolic geometry, sort of bounds on hyperbolic metrics, in terms of coefficients, but they're a little bit complicated. There are other, if it has this form, then something statements here and there, but it's really not well understood what the geometric content is. Yeah. It's a great question.
Is there an easy way to tell if you have an alternating diagram if it is non-stupid?
Yeah. How do you tell if your alternating diagram is non-stupid? You take a little arc that's transverse to each crossing. Maybe there are 2. You take one there and one there. And you just check if the endpoints are in the same region. If they're in the same region, then it was stupid, and otherwise you do it for all the crossings, it was not stupid. Yes, this is easily computable. That's always a good question to have in mind. Yeah.
Can you give an example of a non-alternating diagram?
I can give you both a non-alternating diagram and a knot that doesn't have any alternating diagram. So I can make this one non-alternating by just adding a little kink to it. So here's a non-alternating diagram for a knot that has an alternating diagram. Many knots also don't have alternating diagrams at all. The one easy one to write down is the 3-4 torus knot. So 1, 2, 3, 4. Whoops. Doing great. And here's a knot, T3-4, maybe, and it has no alternating diagram. Yeah.
How do you connect?
By the way, Tate asserted that all knots have alternating, or believed that all knots had alternating diagrams for like 30 years. And then he has a sort of funny note where he says, oops, I noticed this is not true in a later paper. Again, his papers are great, but
How do you connect the Jones polynomial to the crossing number? Or I guess I'll ask.
that's a good question. How do you prove this theorem, or why are they related? You can sort of see that how wide the Jones polynomial has something to do with the crossing number, because like how big can this be is the crossing number. That's the crossing number. It's a number of possible ones, and how big this could be has something to do with the crossing number also, because that tells you something about the number of circles. So the crossing number is sort of sort of showing up in that formula. Proof's not immediate. Yeah. Oh, good question. No, so you'd think that. I'll give you another old question that's related. Here's an alternating diagram with an odd number of crossings. I'll tell you why this is not a contradiction mathematically after I convince you it's alternating. Over, under, over, under, over, under, and we're back. And the point is you go through each crossing twice before you get back, so you don't get a parity problem. There was a question for a long time. So this knot is not the same as its mirror image, but some knots are the same as their mirror image. And there was a question for a long time whether any odd crossing number knot was the same as its mirror image. It's called being amphichiral. Because the first examples where it happens have like 13 crossings, and just nobody had seen them. And the answer is yes, it happens. It's rare for small knots, but that was an open question for a long time. So that doesn't happen for alternating knots by a version of this theorem. So there is, this happens, but there's other stuff that's related that doesn't for sort of the reason you have in mind. More questions? Yeah. Is there a good way to tell if a knot doesn't have an alternating diagram in general? The short answer is no. There are things that are special about like the Jones polynomial of alternating knots, the Alexander polynomial of alternating knots. So if you don't have one of those properties, you don't have an alternating diagram. But the converse is not true. You list out all alternating diagrams up to 19 crossings or whatever, of which there are some number of billion. And not diagrams, knots, each of which has many diagrams, and then you start check laboriously if yours was on that list. It's not a problem that has a good solution at the moment.
Just to be clear, in an example like this where you have a stupid knot, when you resolve that stays alternating, right?
It does stay alternating, or at least it can stay alternating. Yeah, I think it does stay alternating.
I was wondering, because that would mean that given this theorem, if you wanted to prove that something didn't have an alternating diagram by brute force, you could find a simple diagram and try to figure out. Well, I don't know.
You have to look at all simpler diagrams, and then you have to see whether you could transform yours into it. Here's a much easier question. If I give you a knot, is it the trivial knot? Actually, let's have a conjecture. Here's a conjecture. Vk of q is q plus q inverse if and only if k is the unknot. So that's open. So maybe you could just compute this Jones polynomial that tells you if you had the trivial knot, but that's not known. More questions? Okay, let's not erase that. Let's erase this. Sorry, conjecture. Keep that conjecture in mind. Like, remember that conjecture for like the next 25 minutes. Part 1, Khovanov homology. So there are two ingredients to define Khovanov homology. One of them is this cube of resolutions. Cube of resolutions. Well, you see, it's a cube of dimension equal to the number of crossings. So here we had a square of resolutions. There's a square of resolutions. If I had a 3-crossing diagram, I would have had a 3-dimensional cube of resolutions, and otherwise some higher dimensional cube. So that one we did, check. And the second thing is I need a ring. So I need a useful ring. So we're going to do that for the next 3 or 4 minutes, then we'll get to the actual definition. So my ring I'm going to call A, and it's Z adjoin X mod X squared. I think I said all you need to know is abelian groups, not rings. It'll be OK if you don't know rings. I'll come back and make things more precise, more down to earth in a minute. But this has a multiplication. So what is a multiplication? It takes a pair of elements of A, and it gives you a new element of A in a bilinear way. So for example, m of 1 and 1 is 1, because if I take 1 times 1, you get 1. M of 1 and x is x, and so on. M of x and 1 is x. I'll just write everything out. And if I multiply x by itself, it's 0. I think this is a capital X. I think I'm going to use a capital X there. So if you can't tell, that's a capital X. Because I just by fiat made it equal to 0. This ring actually has also a co-multiplication. So that takes an element of the ring and gives you a pair of elements of the ring. And I'm just going to define that by formulas. It's given by delta of 1 is 1 tensor x plus x tensor 1, and delta of x is x tensor x. If you take the cohomology of a smooth closed-oriented smooth manifold, it always has a co-multiplication coming from Poincare duality that's sort of sketched on the homework, and this arises from a sphere, even-dimensional sphere. M is associative. It has a unit. So I'm going to say has a unit. Delta is co-associative. It's a co-multiplication. So you just put co before things. It's co-associative, and it has a co-unit. The co-unit is not actually going to matter for what we're saying today, so I won't dwell on it much. And M and delta are related. So M and delta satisfy the Frobenius relation, what I call the Frobenius, we'll call the Frobenius relation. That is that delta circle M is equal to M tensor identity composed with identity tensor delta, don't panic, which is identity tensor M composed with delta tensor id. OK, what on earth? So I'm going to read from top to bottom, and I'm going to think of M as something which has 2 inputs and gives 1 output. So if I feed in, for example, 1 and x, I get out x. This is M. And delta I think of as having 1 input and 2 outputs. So for example, I feed in x, you get out x tensor x, x then this bizarre relation I just wrote down says that if I do m and delta, that's the same as doing nothing to the first thing while I split apart the second, and then I merge these two while doing nothing to the last factor. And that's the same as doing it in the first factor. Again, it's not so important for the rough outline of the rest of the definition, but I just wanted to tell you that m and delta interact in a nice way. And I'll tell you later in a minute where that comes up. So now what I'm going to do, so that was the end of the algebra. I'm going to take my cube of resolutions. So take cube of resolutions. OK, here is cube of resolutions. I'm going to replace each circle is going to turn into a copy of this ring, abelian group, whatever, A. Disjoint union I'm going to turn into tensor product. So again, I'm going to make this a little more concrete in a moment, but let's start doing that because it'll help. So in my cube of resolutions, I had, at the 0, 0 vertex, I had two circles. So I have A tensor A. At this vertex, I had one circle. Here I had three circles. And here I had two circles. If you do that equivalently at each vertex V, I have the free abelian group generated by all ways of labeling circles 1 or x. So for instance, here I could label both circles 1, or I could label the first one 1 and the second one x, or I could label the first one x and the second one 1, or I could label them both x. So I've got z to the fourth over here. I'm going to write out in gory detail what that all is. So this is 1 tensor 1, 1 tensor x, x tensor 1, and x tensor x. Here I just had one circle, so this could be labeled 1 or x. Here I have 2 again, so this was 1 tensor 1, 1 tensor x, x tensor 1, and x tensor x. And just in case it helps in a moment, I'm going to try to be consistent with my notes in order of writing things. Fine. 1 tensor 1 tensor 1, 1 tensor 1 tensor x, 1 tensor x tensor 1, 1 tensor x tensor x, x tensor 1 tensor 1, x tensor 1 tensor x. I apologize for, making you watch this. X tensor x tensor x. Okay. These are the basis for my abelian group at each vertex. Now, you might have noticed I sneakily drew edges on my cube. I make look more cubey. I'm actually going to make the edges run from 1 to 0. At each edge, one of two things happens. Either a circle splits into two circles, or two circles merge into one circle. Okay. So if what happened was a merge, I'm going to apply the operation M. And if what happened was a split, I'm going to apply the operation delta, the co-multiplication. So here, two circles merged. So this is an M. Here, a circle split. This is a delta. Here, oh geez. The first circle split, the second circle didn't change. So I'm going to apply a split, and then the last circle doesn't change. Whereas vertically here, the first circle didn't change, and the last two circles merged. The second and third circles merged. What? I'm going to do that in gruesome, gory explicitness. The multiplication map, x times 1 is x, 1 times x is x, and 1 times 1 is 1. Okay. The split map, 1 splits to 1 tensor x plus x tensor 1, and x splits to x tensor x. What? This is, I wrote it down right there, right? I'm just applying that formula. Yes? It is just a Frobenius relation. Good catch. So you've noticed I can draw a little commuting symbol there by the Frobenius relation. I'll say that again for everybody else in just a sec. Let me finish annoying you by decorating this picture. The first circle isn't changing, and the last two are multiplying. So this goes to 1 tensor x. This goes to 1 tensor x. This goes to 1. Again, the first circle isn't changing. So this goes to x tensor x. This goes to x tensor x. And this goes to x tensor 1. And finally, here was happening the first circle. So this goes to x11 plus 1x1. And this goes to x1x and 1xx. And this is so much fun. OK, the first one is splitting into x's. This is xx1. Well, and this is xxx. OK. Super concrete, we can agree. Could get a computer to do. Yes?
What happens if instead of allowing two choices for what you label the circles, let's say you say that you can also call them y, or you have 100?
That's a great question. Let me punt that a little bit till we get a little bit later on. But ask me that same question just that way in about 15 minutes. So far, nothing breaks. OK, well, there you have it. So this cube commutes. Exercise. In the sense I put on the homework. Well, there are various kinds of faces. You could have a merge and then another merge. You could have a split and then another split. You could have a split and a merge and a split mixing like this. And depending on what the face looks like, either it's associativity of the multiplication or co-associativity of co-multiplication, or something happening, two different things on different parts of the diagram, commuting, or this Frobenius relation that we just saw in this example. So great. So there's a standard way to take a commutative cube of abelian groups and get a chain complex from it. So I'm going to say that very briefly, and I'm going to say it in a more long-winded fashion, as you should expect at this point in the talk. You can take its mapping cones repeatedly. So take the iterated mapping cone. That gives you a chain complex. Its homology is Khovanov homology. Let me say that more concretely, because I've been doing that with everything. This commutes. I'm going to add signs to some edges to make it anti-commute. So add signs to make anti-commute. And there's a very concrete way to do that. You multiply the map on an edge v1, v2, vi minus 1, 1, vi plus 1 through vn to v1, v2, vi minus 1, 0, vi plus 1, vn. By that. By minus 1 to the v1 plus up to vi minus 1. Okay, so there's just some universal sign you multiply some of the maps by. And in this simple example, that means I put a minus sign right there. Okay. This lack of moving boards is becoming a real problem. Now, the Khovanov chain group CKHI is the direct sum over vertices V with absolute value of V equal to I. Remember there were this funny q to the n minus at the, or sorry, I to the n minus at the earlier things, sorry, minus 1 to the n minus. So I'm going to actually write I plus n minus. This is just some shift to get it to behave well later. Of the thing I wrote at vertex V. Let's write A of kv. This is the group at vertex V. Then the maps on edges, I'll do this in the example, it'll all be clear, give you a map CKH I to CKH I minus 1. I'm going to call that boundary sub I. Boundary I composed with boundary I plus 1 is 0. That came from the fact that the faces, that each face anti-commutes. Again, I'll write down the matrix for this in just a sec, but I want to give you the definition for some reason now. So I can then define the KHI of k is the kernel of boundary I mod the image of boundary I plus 1. So I've now given you a complete definition except for one of the gradings of Khovanov homology. What I'm going to do is I'm going to show you an example. So for example, that's what it looks like for the trefoil. That's for this knot. Some groups, some z's, some z mod 2's. This is I. I haven't explained this axis yet. I'll do that maybe at the very end, given how time is going. I want to do this collapsing thing, CKHI, for that example. So in that example, I have CKH minus 1, CKH 0, and CKH 1. Again, the shift is because n minus is 1, and I stuck in a shift here. Don't get excited at the absolute labels. This was the sum over absolute value of v equal to 0. That's this group. The next one is this, and the next is that. I take the direct sum. So this is A tensor A. This is A tensor A tensor A plus A. And this is A tensor A. And our maps are the maps I wrote down over there. So this is the identity tensor M and delta. And this is a column matrix given by delta tensor id and m. And I lied, it's minus m. We put in, that's the minus sign I put in over there. And if you multiply these matrices, you get 0 because this whole thing anti-commuted. That was some asserted exercise before. Then I look at the, here I've got 0. Here I've got 0 before this. I look at the kernel of this map. That's all of this. Mod the image of this map. That's the group here. And the kernel of this map, mod the image of this map. And that's the group here. And the kernel of this map, that's the group here. Okay. In the remaining 2 minutes, I want to do 2 things. I want to tell you the second grading just so you've seen it on the board. So the second grading, the 1, 3, 5, 7, or 9 is, I want to do 3 things. N minus 3n minus plus absolute value of v plus the number of x's minus the number of 1's. I'll compute that in the question session for an example if somebody wants, and otherwise I'll compute it maybe in 2 weeks. The theorem of Khovanov is that up to isomorphism, these groups are unchanged by Reidemeister moves. So this is actually a not invariant. And you can sort of see it's got the Jones polynomial difference. You can sort of see shadows of it here. So a second theorem is that if you take the right sort of Euler characteristic, you get the Jones polynomial. The last thing I want to do is I want to compute it for this example. I'm going to do that by taking subcomplexes or quotient complexes with trivial homology, acyclic sub and quotient complexes, and just deleting them. For example, these 2 terms form an acyclic subcomplex. There are no arrows out of this part. There are arrows into it. And they cancel. I look at the kernel mod image just for this arrow is 0. So I can erase them. And those arrows went away. Let's see if I can find some others. So this and that form an acyclic subcomplex. And quotient factors summand. So let's get rid of them. This and that is not a subcomplex because there are arrows out of this, but it's a, no, there isn't actually anymore, is there? That's just a summand again. So that and that I can cancel. All gone. What else have we got? 1 and this x tensor 1, that forms a subcomplex, so I can kill off those 2. Those are gone. It's gone. Let's see. There are now no arrows out of this. So this and that form an acyclic quotient complex. So they're gone. And this and that form an acyclic quotient complex. So I can erase them. And let's see. This and that, that's an acyclic, well, it's an acyclic summand, sub or quotient, you choose. And I don't know, this and that is an acyclic sub, so we'll just get rid of that too. Ta-da, there was the Khovanov homology of the unknot is isomorphic to z squared, and it's in grading 0, by grading 0, 0. Sorry, well, no, in by grading 0, 1, and 0, minus 1. This is like the q plus q inverse that we had before. Not direct sum, plus. OK, so that was too fast to follow the computation. I'm happy to go through it slowly with people who want later, not even during the questions. Maybe sometime later if you want. But I think it makes it clear this is very concrete to compute. It's not hard to compute these quotients, subs and quotients. OK, I am 1 minute over. I will stop there, and we'll start again in a week. Thanks for listening.